very significant because it's a precursor to what we might see coming from the Event Horizon Telescope. This report came from the Gravity collaboration. Gravity is an instrument on the very large telescope in Chile that the Europeans have. It's actually two telescopes that operate as an interferometer. It operates at 1 micron wavelength instead of a millimeter like the Event Horizon Telescope. So you have 1 micron wavelength, but we're talking about the separation between the two legs of the interferometer of order tens of meters. So the resolution is not good enough to take the wavelength over the diameter of the observatory. It's not good enough to obtain an image of the silhouette of the black hole. But this gravity instrument is allowing to find the centroid of the light to an exquisite precision of tens of microarc seconds. And so what they did, I mean, they have a previous paper detecting the gravitational redshift from a star orbiting the black hole, which by itself is an interesting anecdote, but nothing new. I mean, here they report the orbital motion of a hotspot near the last stable orbit, so roughly at 7 to 8 GM over c squared. And the way they detect it is, think about a flare, just like on the surface of the sun, where magnetic fields reconnect and heat up the plasma. You have a region which is hotter than the rest, has a higher thermal pressure, probably less magnetic field pressure. And as long as that region survives, you can monitor its orbit around the black hole. And they report a motion of the centroid of the emission, of infrared emission, at roughly 7 to 8 GM over c squared. So if we can scroll down, I'll just show you two of the key results. And that's quite remarkable. They see the hotspot moving on the sky, roughly on a circle, which means that we are looking at an almost face-on equatorial plane. Let's go scroll
Isn't
down.
that surprising?
Well, it's not exact. It's like 20, 30 degrees is consistent. So you can see here, it looks like almost a circle. And by the way, the orientation is consistent with the plane of, there is a disk of stars, at tens of thousands of Schwarzschild radii from the black hole. And it's consistent with the gas being fed from those stars, because the plane of the orbital plane of those stars is consistent with the orientation of this.
That plane is 30 degrees out of the plane of the galaxy?
Yeah, the galaxy has nothing to do with filling the black hole. It's just the vicinity of the black hole that is filling it. The stars in the vicinity that are filling it. And
it doesn't look like a 30-degree tilted circle.
Well, it doesn't, but look at the error bars. This circle, you're right, yeah, but the error bars are big. So they're trying to fit, I mean, it's a clockwise motion of the hotspot. By the way, they see 3 flares, and in each flare they can follow the hotspot for roughly half an orbit. And you may ask, what happens to the hotspot afterwards? There are 2 possibilities. One is the electrons cool. The cooling time is comparable to the minutes time scale for the orbit. So either the electrons cool or it's sheared out, because differential rotation basically shears the hotspot. If we can scroll to another plot, I just wanted to show you. So this is truly groundbreaking. I would say this is a breakthrough in, for the first time we see source of light moving near the ISCO, near the innermost stable circular orbit. Continue to the supplementary material. Oh, they also, what you saw there was the polarization. They also measured the polarization angle. And they determined this, just for a minute, this shows the period. So they can measure the period, the orbital period, at the same time that they measure the angular size of the orbit. And since we know the mass of the black hole, you can compare it to either a zero spin black hole, the Schwarzschild case, and this is the innermost stable circular orbit for the Schwarzschild. You can see the 3 flares here. So it's consistent with a zero spin black hole. Here is a maximally spinning black hole, but a hotspot orbiting opposite to the spin of the black hole. So a retrograde orbit would also be consistent. So they are talking about 2 possible likely situations. One is a Schwarzschild black hole, and second is a rapidly spinning opposite to the orbit.
What, you can't have any spin?
Sorry?
What's
Yeah.
special about could you have spin a half?
Oh, it's just that it doesn't match. I mean, they claim that the best match they find is for these two cases. I mean, you just have to look at the data.
The details of the data.
Yeah. So they do, you know, an MC analysis of all the parameters, including the inclination and so forth. If we continue further, more, until we get to the plot. No, another. More, the last one. Yes, this plot. So this plot shows you the contours for the inclination. So you can see that it's not really zero. I mean, the island of the highest likelihood, the peak of the likelihood is, you know, it could be 40, could be 30 degrees.
Does this assume the spin is zero?
This was A equals 0. So you can see here they constrain the radius of the hotspot, orbital radius, and they say that for r greater than 6 gm over c squared, the constraints here are for 0 spin. And for smaller radii, the constraints were derived for a of minus 1, or a of 1, a retrograde orbit. And you can see that, you know, it's quite remarkable that we see the hotspot just outside the innermost stable circular orbit for a Schwarzschild black hole. It means, you know, that's the last place you could find it before it plunges straight in. And that's also the brightest region. So I'm sure there will be follow-up work, and this is a new test bed for general relativity. I mean, it's different from LIGO. We're not using gravitational waves, but we are probing the same region of space-time. And the reason I'm particularly happy about this is that in 2005, we wrote a paper, if you can just, with Avery Broderick. Back then, the EHT was just starting with Shep's effort. And what we did was ask, what would a hotspot look like if there is a flashlight, you know, the simplest model of a region that is bright, moving around the black hole. What would it look like? That was the first calculation, and many of these predictions are being used by the observers now. And you know, it's the best satisfaction that a theoretical physicist can have, to predict something and then 12 years later, 13 years later, experimentalists confirm it with data. I didn't expect suddenly this email over on Saturday. I didn't know that they are getting to the level of precision that they are. But we will hear a colloquium by Frank Eisenhower, who is the experimentalist that is responsible for gravity, and he's been labeled as a genius instrumentalist, in the sense that this instrument is really a state-of-the-art accomplishment. And I hear from him, so I congratulated him this morning, and I heard back, he said that they have a third paper currently reviewed in Nature about 3C273. So wait for more results from gravity. It's quite a remarkable instrument. And
I should just mention while you're on this that Graham of South Carolina also did the image for a hot spot for A equals 1, but for the prograde, not for the retrograde. Wouldn't be hard to redo it for the retrograde.
Yeah, so now it would, just like with LIGO, I think it's a new test bed of general relativity, and you know, future data would probably be much better. So anyway, that's all I wanted. Yes?
If I may comment, this first paper is also quite interesting because they are comparing the redshift for a Newtonian orbit and non-Newtonian orbit. They're testing GR as well in some sense, right? It's not only the it's something more.
Right. And it's a different test than gravitational waves provide us. Because these flares happen all the time. It's just that they looked at 3 of them.
Are they actually seeing the radius? They can resolve the radius?
Yeah,
And
what they
of
see is the
6M?
centroid of light doing a circle on the sky.
So they have an angular resolution of just 6 times the size of.
No,
a
they
center
cannot
star.
resolve the image of, as I said, they cannot, so they have
Well,
a
what
point
was that
spread
picture?
function.
It looked like you had a picture that was.
Okay, think about a mountain. You can localize the top of the mountain extremely precisely, but the mountain is much broader. Okay, so the light distribution is very broad. They cannot see any image, but they can localize the centroid of light extremely precisely, and they see it moving in the sky in a circle. That's all.
Well, then how do they know it's at the ISCO? How do they know
Well,
it isn't at twice the ISCO?
Well, they see the circle on the sky. The centroid is moving in a circle, so there is a center to that circle, and it's right where Sagittarius star is supposed to be.
But you're saying you can resolve the center to within 6M? To within a couple M?
Yeah.
How do they know the thing isn't orbiting at 12M?
Because they see, they can tell
They
the
are
difference.
resolving
They
to
are
better
resolving
than-
for the centroid.
They
But
are
not,
resolving better than
yes,
6M.
but for the centroid, the precision they reach for the centroid is tenths of microarc seconds, while the point spread function, the distribution of light is much broader than that.
Right.
So that's the idea. So they didn't really get an image, they got motion. They can see a movie, they can see the motion.
And would we expect they just happen to be looking at microns? Would we expect that if we looked at other wavelengths, we'd see all kinds of other stuff?
No, micron is actually not being affected much by gas. So for example, a millimeter gets a little bit of scattering along the way.
You're saying it's fairly translucent,
Yes.
transparent at a micron.
Yes. So
That's where you can see.
you can see all the way to the center in 1 micron. That's a good. That's an advantage of 1 micron. While millimeter, is on the borderline of being opaque and transparent.
Is it transparent between a millimeter and a micron?
Yes. Once you go below a millimeter, things are transparent.
Anywhere below a millimeter
Yes.
is good.
Yes.
I see. So, and if there'd been something at 100 microns, they'd have.
Yeah,
they'd
they could have
it.
seen it. Yeah, in principle. But it's just that the longer the wavelength, the less your resolving power is, because your
Right.
interferometry is
Right,
not over D.
right. So maybe they wouldn't have at 100.
But what you want actually is to have an interferometer that is 100 meter in diameter or 1,000 meter, which is something people are contemplating now. And take 1 micron divided by that scale, that would become quite comparable to the EHD. So right now it's not, they cannot see an image, but in the future they might. That's something to watch out for. So we are all waiting for the EHD announcement. Once everything is done, it will obviously be different type of sciences. We will hopefully get some sense of the image, and also a different source perhaps.
So everyone, our first speaker today is Michal Bejger. Michal is currently on sabbatical from Copernicus Center in Warsaw, working at the Royal University in Paris. He is a member of the Virgo collaboration and a specialist on neutron stars. And he will tell us about possibility that fast radio waves are actually primordial black holes hitting neutron stars.
Okay, thank you for this invitation. I will talk about kind of a fun project that we have with Mike Abramovich. This is this kind of project that you ask, like, what if fast radio bursts are collisions of come from collisions of neutron stars with primordial black holes. So let me make a little bit of introduction and then I will talk about this later. So first of all, fast radio bursts. The phenomenon is not new. It was first described in 2007, but actually using the archival data from the beginning of the century. And they are called fast radio bursts because they are very short. Duration is of the order of 1 millisecond. They are in radio. They were not observed in other wavelengths. That doesn't mean that they are not occurring at other wavelengths, but maybe the detectors are not well designed to detect such short bursts. For example, X-rays, you don't have such a resolution, maybe, to detect them from far. they occur at cosmological distances. This is inferred from the dispersion measure, the way the pulse is being dispersed by the column of electrons on the way. And this dispersion measure that is measured on the radio telescope is much larger than the one that is supposed to occur within our galaxy, so that's why it's the cosmological distances. And from those detections that are basically done by chance, because the radio telescope was just pointing somewhere and then there was a burst, one can infer occurrence rate, and this occurrence rate is of the order of 1,000, so on the sky per day. So this already is quite interesting. The flux is of the order of Jansky, and there was also a polarized emission measure. So to me, I was working a little bit with neutron stars. This kind of suggests that this has to do with some magnetic fields, and maybe this time scale also is related to the neutron star size kind of time scale. So most of them are one-time events, at least this is what we see. But there is one that is repeating. This one kind of stands out, and this is this one. And so far, several, or maybe actually tens of bursts were detected from the same source. And the source is quite peculiar. It is related to a dwarf galaxy, kind of a young starburst galaxy full of gas at 1 gigaparsec, so it's really cosmological. The bursts occur in a completely crazy fashion. This is not periodic, not even Poissonian, some kind of a clustered emission of bursts. Maybe that for a couple of days it doesn't do anything, and then there are several bursts during 1 hour. And one can estimate the energy. The energy is like a moderate amount of energy. It's not small, but you have to have a mechanism to produce sustainable several or tens of bursts with this order of magnitude. So this is an interesting question to ask. What can it be? And so this is basically the slide why this is interesting. Because we have a very frequent, very short duration. The short duration is actually, I think, one of the shortest duration astronomical events that we can actually observe, or we are observing. Usually in astronomy you have longer duration events. It's quite energetic, and there is no clear origin. So there is a myriad of ideas. Of course, it can be extraterrestrial intelligence. I think it's a possibility, right? Or, well, I didn't put military here, but it could be also military. Let's say that's not military. Then there were all kinds of models proposed for this. It could be that they are related to the merger of compact objects, like black holes, neutron stars, mixed events. Other propositions were about that these are actually quantum, actual quantum black holes that are actually now exploding somewhere in the cosmos, Planck stars or Planck black holes. Collapsing neutron stars, and especially energetic supernovae, could produce something.
These models were proposed before the repeater was discovered, is it?
Yeah.
Many of them are incompatible with
Yes.
a repeater, right?
Yeah. So then people are using this kind of logic that okay, there may be like 2 classes. One is repeating, one class is repeating.
But the one that is repeating is the only one we know the distance to.
Yeah,
sure.
Yeah. So, and then we are kind of subconsciously basing our models also on this one. For example, energy is actually well established because of this one and so on and so on. So everything is kind of mixed. Yeah. But for example, this one could be a repeating one. I mean, that's one.
Yeah.
Yes. Yeah. And the accretion, so on, super relevant. So I know that this is a kind of weak argument, but people are saying, let's assume that there actually are 2 classes. One is repeating, one is not repeating. Okay. How come we didn't prove that? We don't know how it is, right? So this is, I think, this is one of the biggest mysteries. This faster burst is quite a peculiar phenomenon, and so frequent. You might have like on the sky like thousands per day. Like, what can it be? So I will now continue with the introduction and talk a little bit about dark matter. So there is this big question: what is the total mass energy of the universe? And basically, the bottom line is that we are living in a universe that basically we know 5% of, and everything else is some kind of a mystery, either dark energy or dark matter. And this dark matter is known from the fact that when you observe rotating disks of galaxies, they don't rotate as we expect them to do, judging from the luminous matter, but they rotate as if there is some kind of another potential halo, dark matter halo, in which this luminous disk is rotating. So this dark matter is kind of surrounding the galaxy. And it can be composed of things. For example, it can be composed of new type of particles that we outside the standard model, or it can be composed of massive objects like black holes, for example. It's one of the ideas. I'm not saying that it's like that, but it was one of the ideas. And so we know about stellar mass black holes. Stellar mass black holes were proposed as the solution to the dark matter problem. Now we know that it's not like that. But several years ago, we, for example, didn't know that stellar mass of the order of 30, stellar mass black holes of the mass of the order of 30 solar masses or larger, or 60 solar masses can exist before the LIGO detection. So we have some kind of a mass function of black holes. They can be really massive. They can be really massive, like the Sagittarius A star or galactic center of galaxy black hole. They can be of a stellar mass size. They can be, for example, like this one. This is the GW170817 that most probably is a black hole within the mass gap. But of course, they can also be a smaller black hole in principle, because so far we didn't rule them out. So, and then if we allow us to speak about the whole spectrum of masses, then we can look at such a diagram. And this is one of those diagrams that show you the limits on the observational limits on black holes of different masses. So this is to the 10 to the 15 grams, and this is more or less the size of the sun, mass of the sun. Black holes created in the early universe of masses lower than 10 to the 15 grams would already evaporate until now because of the Hawking radiation. So smaller masses are excluded. So black hole of the mass of 10 to the 15 grams has a kind of an atom micron size or something like that. It's very small. And then, so we have limits on the Hawking radiation, evaporation, femtolensing, collisions with different objects like neutron stars, white dwarfs, and then microlensing constraints, and then more massive black holes are constrained by observations of cosmic microwave background, accretion, and other things. So it is kind of obvious that black holes from this spectrum of masses probably cannot really be used to explain dark matter. But maybe they are consisting of part of dark matter. For example, this region, like here, this is 1%, oh sorry, 10%. So maybe they are there in the halo. They are not fully explaining dark matter, but maybe they still are not ruled out. So I will be speaking about such a poorly constrained range of primordial black hole masses. This is the poorest constrained range, which is, for me, a theoretician, is a perfect opportunity to fantasize about what can happen if they really exist. Okay. So, and I will also be speaking about neutron stars. So this is a slide about neutron stars. The most relativistic objects we know, and the most dense, the densest matter in the universe currently. They are extreme in many ways. They have very powerful magnetic fields, macroscopic, superfluid, and superconducting bodies. And they are basically very often found in many situations. Supernova remnants and in mergers. Currently, we know that they can occur, and so they are born in supernovas. We observe them as pulsars. This is the period derivative period plot. They are born somewhere else, somewhere here, and then basically slow down as pulsars. At some point, they stop being visible as pulsars because they rotate slower than critical frequency to produce current, produce the radio emission. So we currently see more or less a couple of thousands of neutron stars as pulsars, but in principle, from evolution, there should be more of them in our galaxy and in every galaxy. And we know not very much about their interiors. We know that they have some kind of a crust that is more or less 1 kilometer thick, that consists of matter that is below the nuclear saturation density, and then below, above this density, this other 10 kilometers of the star is denser than nuclear saturation density, and it can be magnetized superfluid matter with some exotic components. So this magnetized object has a size of more or less a couple of kilometers, tens of kilometers, and it contains a lot of magnetic field. So if it's hit by the black hole, it may produce a desired energy and duration of radio radiation. Okay, so now we'll be talking about this fun project. So basically, this is it. What happens when the neutron star is hit by the little black hole? So imagine something like that. We have a halo of black holes in the galaxy, and from time to time, this primordial black hole is hitting a neutron star, and actually it hits it, and it most of the time it flies. I mean, it goes in, but then it goes out because when one calculates the velocity of primordial black holes in this halo, they are actually quite large. So it will hit it, but it will go away, but at some point it will be dragged back because it will. I mean, it will lose a little bit of energy, but the velocity after the collision will be smaller, so it will have to go back and actually it will settle inside the neutron star at some after maybe several collisions. It will go in and stay there, and then it will start to accrete the dense matter from within the neutron star, and this accretion process and the subsequent collapse is related to the fast radio burst. This is the one slide that does this.
Are you assuming Eddington limited accretion here?
This is a very simple.
Because the Eddington time is 10 to the 7 years.
So we are assuming some kind of a simple Bondi accretion here. Of course, it can be elaborated.
Yes, but what is the time scale for eating up the neutrons?
I will show you. Yes. But first of all, I will talk a little bit about this model of simulations of how many collisions we expect and whether this is consistent with the observed rate of fast radio burst. So we have a very simple model of the galaxy, like that. And we are considering several species, neutron stars, primordial black holes of the mass of the neutron star that are produced by the collision and the accretion, and then some larger black holes, like that. And so basically one has to solve a bunch of equations that in which we have creation and destruction of, taking into account the evolution of species that are being created by collisions or being born from supernovas like neutron stars. So we have several conditions like that. So if there is one species that is less massive and the other one is more massive, the more massive one is attracting the less massive one, and then if the velocities of them match, then the one is trapped and we have a collision. And of course, we have to assume some kind of a simple creation rates. So we are, for example, assuming for neutron stars and stellar mass black holes some kind of a typical creation rate of supernova ray. So we are solving some kind of an set of equations like that. It's kind of like predator-prey type of equation, but not really. So the neutron stars are being destroyed in collisions, but also they are being created. Primordial black holes are being only destroyed because we assume that there is a primordial gas of them, light black holes, and so on and so on. And then these are our results. Depending on how big the ratio of the primordial black holes to the total dark matter halo is, we can get different rates of fast radio bursts, and it also goes with the mass of the primordial black hole. But basically, by playing with the mean mass of the primordial black holes, because we don't know what's the mass function, we may get what we want, assuming that we are observing fast radio bursts from the whole universe. We have to multiply this by this, and then we will get something of the order of 1,000 per day. This is again a kind of a funny thing for a theoretician, because we don't know much, so we can play with parameters. And then we can also have a look at how many collisions per day we have in time. So when we are looking at the past of the galaxy, how this works when there is a number of neutron stars growing in time, and how this changes with the mass of the mean mass of the primordial black hole. So it seems that at the present time we're reaching some kind of saturation. And also there is another one that shows you how many neutron stars we actually expect in the galaxy, being still neutron stars and not light black holes, because we would like to have currently at least 1,000 of the order of 1,000 neutron stars, not less, because it would then contradict our observation. But it works. If we look at the simple model, then basically we could get this result like that. But principally, it's not contradicting the observation. Okay. So then, what about the energy loss in the passage? So the primordial black hole enters the neutron star. It loses a little bit of energy. It goes out, but it doesn't fly very far. It doesn't fly onto the distance of the order of a parsec, but actually closer, and then it comes back, hits the neutron star again, and goes back and so on, and then after several collisions, it settles. So one can do this. This is just for a couple of masses, but in principle, it should work for a range of primordial black hole masses. So we assume that basically once it hits the neutron star, it always goes back and then it settles.
Is that reasonable? Seems to me that this fellow will come and he'll hit, typically it'll hit off center.
Well,
It may kind of bounce off in some other direction, or it may be a spinning neutron star. I can imagine lots of reasons why when it comes back, it may not hit it. It may go into some kind of a funny orbit.
Yeah, it will go. So then it will go on the orbit, and then it will induce some energy loss on the neutron star. It will radiate a little bit of gravitational waves, and it will go back. Right?
Okay.
I think you wrote a paper.
Yes.
About
I
that.
wrote the paper, but we consider the modes that are excited in
Yeah.
the neutron star,
Mhm.
and not the formula that we use.
Yeah, this is very simple. This
Right.
is the, as
So it's
simple
not
as-
friction, it's not collision or accretion of matter. It's basically we consider the excitation of modes, which dissipates energy from the orbit and brings it back.
So we here assume that basically the velocity of a primordial black hole in the halo is of the order of speed of light, and to be as simple as possible. But once it hits it, it loses around 10 to the 40 something ergs. Then it goes back, and then if it would fly further than a couple of parsecs, then probably it would be lost. but it's not. So this is a very simple. Okay. But now about the accretion. So once it's inside, then it starts to accrete, and basically what we assume is a kind of the simplest thing is a kind of a Bondi accretion, and one can get at some kind of a time scale. And to me it was a surprise because in the beginning I thought that once the black hole is inside the neutron star, basically it will immediately collapse. But it can take some time depending on what's the initial mass of the primordial black hole. It can even take years. So the idea is, this has to be checked of course, that it starts to accrete, and it accretes matter, but it also accretes magnetic field, and this reconnecting magnetic field is the origin of the repeating fast radio bursts. So when this mass is larger, then basically it accretes fast, and then there is only one final burst connected with the horizon appearing and the object getting rid of the hair. But if it takes some more time, then it may produce several chaotic bursts, and this is basically explanation for this repeating one. Because
that's always with the magnetic field, or?
Yeah. So because in principle the magnetic field may contain enough energy to be a source of many bursts.
How do you get the time scale to be a millisecond?
The time scale is the time scale of reconnecting the field of
And that's a millisecond?
Yeah, because this is more or less the size of the neutron star. No?
Oh, so you have multiple reconnections then?
Yes. So again, we are saying that actually we don't know how the magnetic field is inside. So it may be that there are like bunches of magnetic field in the superfluid because of fluxoid immersed in the superfluid. So sometimes it accretes more, sometimes it accretes less, but some of them are being reconnected. So that would be this. And then the question is, what about the gravitational wave radiation? Because we have a black hole that is accreting a neutron star. Neutron star, let's say, is rotating. It has a quadrupole moment, and then at the end we have a black hole that also has a quadrupole moment. The quadrupole moments are not the same. So we will have a time-varying quadrupole moment, and this is the origin of the gravitational wave. We have to have time-varying quadrupole moment present to expect gravitational wave radiation. So we have estimated the change of quadrupole moment, and actually the time scale, because it may be of the order of years or months. It's a low frequency gravitational wave, and it's and the amplitude of it is not very high. So our prediction is that we will not observe any gravitational waves related to fast radio bursts, if this is true. And there was another paper that was actually kind of a motivation for us, this one, about exactly such a thing, that a neutron star contains a little black hole that is eating it from inside, and then it spins up the neutron star, and then you get mass shedding from the equator, and this may be an origin of part of the arc processes that can be used to explain the abundance. So it's a nice. And then we can always also ask a question: how about the systems in which one of the neutron stars is a neutron star and the other one was converted into a black hole? Because as you remember, there was this event, GW170817, in which one could observe, set some limits on the tidal deformability. So what was measured in the GW170817 was not tidal deformabilities of the components, but a kind of a weighted tidal deformability, weighted by such function of masses that were also not precisely established, but there were ranges. So this lambda tilde was measured, but one can translate this into such a lambda plot, and for the neutron star we assume that we know that it has some kind of tidal deformability. For a black hole, tidal deformability is 0 because it almost doesn't really deform. So we would expect that that one of them should be 0 and the other one should be something else. With this event, it is more or less clear that this black hole neutron star scenario is kind of ruled out, but it doesn't mean that in future events we will not observe something like that. So we can ask a question: how many of them we could see? So there was a very optimistic rate inferred from this event, which this one corresponds to more or less 1% of supernova rate, which is kind of high. But okay, let's assume that it's like that. And then we could take one of the numbers that is more or less for this mass. FRB rate is 10 to the minus 6 per year per galaxy, and then it would mean, if this is true, that one, let's say in 100 of such mergers should contain a light black hole and a neutron star. So, in principle, this is a way of checking whether this is possible, because we didn't so far didn't observe such light black holes in our galaxy. Okay, so I think this is more or less the end of my talk. I just have a summary like that. So this bottom line is that this is not excluded. I mean, it may be that for a moderate rate, I mean, a moderate fraction of dark matter consisting of primordial black holes of a specific. In principle, it could be like that. And then one could also always play with this, like, there is a mass function, and then for larger masses we have one time event, but for smaller black holes we have it takes some time to accrete, so it may stay for some time and then accrete to magnetic field, and then we'll have a repeating one. The gravitational wave emission from such a process we estimate that it's not very likely to be observable, because in our galaxy it doesn't happen too often, and in cosmological distance it's too far to observe. But maybe we could observe it on cosmological distances when there is a system of neutron star and black hole. So, thank you for your attention.
Other questions?
I have a question. When you say that all but one have distance undetermined, does that mean there's no idea about their distance? I mean, are they local group, galactic, very far distant? I mean, do we have any idea?
So there is only this one that we know that the distance, and then there is usually the dispersion measure that is large, right? So if we believe that they are of the same class, then we can say that those that have large dispersion measure, I mean of 1,000, let's say, then they are of several gigaparsecs. And yeah, but this is not the direct measure.
Any other questions?
Yeah.
Yes, here.
Oh, sorry.
So the size of a neutron star is 10 kilometers, roughly the size of Boston. Okay? The size of the Earth is much bigger than that.
Yeah.
Okay. There are many more Earths than neutron stars.
Yeah.
But let's focus on ourselves. So how frequently does such black holes pass the Earth, and what damage can they do?
I think they just go through. Because
Well, it's not negligible.
Because the density is not high enough to stop it.
Not stop it, but the gravitational pull can kill the dinosaur.
I think there was such a paper.
So Abby, when we started simulating that, I had this terror of like, how come it's like, could there be millions of those tiny guys hitting planets? And so when I immediately decided to calculate what is the chance for a particular planet to be destroyed,
Yes.
And it turns out that for a particular planet, the expected time to be hit by this primordial black hole and be destroyed is longer than Hubble
Not be
time.
destroyed. I don't want it to be destroyed. I just want it to hit. And since
He just wants to kill the dinosaur.
well, or put a constraint from the fact that there was no major event on Earth over the past billion years. You know, nothing like catastrophe. I don't know.
Yeah.
You should check.
I think we checked that, right? And that
Well, if you have 1 in 100 neutron stars hit, then the Earth should hit very often.
No.
Yeah, but I think that this the Earth matter is too kind of sparse.
I don't think the cross section is so small, and the characteristic density of Earth is much lower
I
than
don't
the
want to trap
density
them.
of
I don't want
Newton's
to-
law.
Because you have this.
Yeah, but you're not trapping them. Just the question of how many times in the history.
But then you don't lose so much energy.
I don't want to lose any. I just ask a catastrophe on Earth. We can have limits on that.
Question is it a catastrophe?
Yeah.
And what Michal is saying is it'll just go through and you won't even know that you're going through.
I guess
Gravitationally, it must pull
they
things.
start the orbit probably. It's,
There will be modes excited because you can't shut off gravity.
So you
right?
say that.
So the oceans might, I don't know,
Yes,
do something.
there was such a thing, and this is actually an interesting question. Like looking for craters on the moon, because we have nice pictures of moon with craters. You can look for specific craters that are on both sides of the moon. and the second one is that it's not the kind of like ingoing but outgoing one, and put a constraint on this. And on Earth, I think on the moon is easier because it's not destroyed by the environment. Yeah.
okay.
And also strangelets and things like that.
So we are a little late already, so let's thank Michal again. And you are welcome to talk to Michal in the afternoon. He'll be hanging around.
Maybe we don't need the first laptops to grab them.
So our second speaker is Rivka Bekenstein. Rivka did her PhD in Technion in physics, in nonlinear optics, and now she's a postdoc at the Center for Astrophysics here in Harvard. And she will tell us about gravity with optical systems and quantum metasurfaces.
Thank you very much. So thank you for the invitation. My name is Rivka Bekenstein. I'm an ITOM postdoc here at CFA. And I will talk today about gravitational emulations using optical systems. So I guess it's a bit different than what you're used to. And I titled my talk From Gravity with Optical Systems to Quantum Metasurfaces. So I will talk today about two different studies. The first one is the Newton-Schrödinger simulator, which was done with nonlinear optics. So this is an experiment I built at the Technion in Israel during my PhD there. And the second study is analog to quantum space-time or curved space, and this led us to this new idea of quantum metasurfaces, and this is a collaboration here at Harvard with Professor Michal Bejger. Okay, so what can we learn from this emulation experiment? So first I would like to define what is an emulation experiment. So what we are doing is we study a system that is analogous mathematically to a different system that we cannot observe, or it's hard to observe experimentally. And why is it so good? What are the advantages? So we have a controllable environment. This means we can tune the parameters in the experiment and maybe access regime that we cannot access experimentally in the real system. We can reveal new phenomena that maybe we didn't know where to look for them. And we can inspire new applications to the emulation system. So these will be applications to optics or quantum optics, as I will mention in the second part of the talk. And I would like you to have in mind these questions. Can we have insight into developing new theories when we do these simulation experiments?
Sorry, but before
Yeah,
you
sure.
Can you
This is me.
translate? Yeah, but can you translate what it says under your photo?
Oh God, that's embarrassing. So it says in Hebrew here that the Israeli state is an empire in the lasers and optics. So this was part of a movie. So my PhD advisor got the Israeli prize, and then there was a movie done. So they came to the lab and they took pictures of us. So this is a picture of me in the lab, and it's a fabricated experiment. It's not a real experiment. It's not my system. I'm just here for the show. So my system was in a different room. Okay, so the reason we can have these tabletop experiments in optics and emulate these gravitational phenomena is based on this analog that electromagnetic fields in curved space are exactly analogous to electromagnetic fields in inhomogeneous optical media. And I will convince you of this idea using one slide. Okay, so here you can see the Maxwell equations in curved space. These are the regular Maxwell equations, you'll know, but G, the metric, enters in each one of the derivatives. Now, Landau and Lifshitz in their book state this: the reader should know the analogy of these equations to the Maxwell equations for the electromagnetic field in material media. We may say that with respect to its effect on the electromagnetic field, a static gravitational field plays the role of a medium with electric and magnetic permeabilities epsilon and mu. And they offer the reader to solve an exercise to show how these equations transform into the regular Maxwell equations in some material medium, where you have a specific connection between this epsilon, the permittivity, and G, the metric. And this is, yeah.
Actually, Ramesh has a review on gravitational lensing where he
We
pointed
use
this
this all
out.
the
Yeah.
time.
He uses it all the time.
Great. Okay. So this is the heart of this field called transformation optics or metamaterials. Transformation optics just means let's exploit this to mimic light in space. And metamaterials say let's fabricate and design materials that have specific refractive indices and then mimic these gravitational effects. And so here are some examples. Okay, so this is from optics. Here you can see two theoretical suggestions of how to fabricate a material with specific refractive index that will mimic gravitational lensing, near-massive stars, or black holes. And here you can see the first experiment done in 2013. So although this is a very old idea, as you've seen, I just read from Lambda and Lifshitz like many years ago, only in 2013 it was possible to technologically engineer a material with specific refractive index where you control the parameters exactly. So everything here is linear, meaning that we fabricate a material and then we launch light to propagate inside and have these specific trajectories. And everything here is classical optics. And I will show you today something that is nonlinear and something that is quantum that relates to this idea. Okay, so what is my own motivation when doing these two different studies? So I like to talk about this triangle of physics where you have special relativity, quantum mechanics, and Newtonian gravity. And we all know that maybe one of the most important questions in physics today is what is going on here? What is quantum gravity? Do we need quantum gravity? So Einstein united for our special relativity with Newtonian gravity, and we have this general relativity, very nice theory. Then we have quantum field theory, unites these two, and we still have a gap here, which is very interesting. So I'm not planning to answer this gap, but my two projects lie exactly here. One of them is the simulator of the Newton-Schrödinger that unifies quantum mechanics with Newtonian gravity. So this is a phenomenological model that takes this equation and put them together. And the other project I will talk about in the second part of the talk is this idea of connecting in some way quantum mechanics with gravity in an emulated system that we can have in the lab. So let's start with the first project. So the idea here is to simulate a gravity for light, but in a nonlinear way. What do I mean when I say nonlinear way? We all know that the space is curved, but the reason that it's curved is because there are masses in the universe. The masses curve in space, but at the same time they travel around the space-time affected by their own curvature, and we want to have this in optics. So here you can see the equation that governs the evolution of laser beams inside some nonlinear material. Okay, and you should believe me, it comes very simple from the Maxwell equation. You can derive it very easily, where you assume you have a preferred axis of propagation. So in lasers, we have one preferred axis, which is the z direction. It looks very similar also to the Schrödinger equation, if it helps you. So we have the evolution in the z direction of psi, the electric field. We have one term which describes the diffraction. So if we launch this, even this laser, it will also always diffract and broaden as it is propagating. And we have here this nonlinear term. This means that if we have an electric field somewhere, there will be a change of the refractive index. So this happens only in nonlinear materials. And then if we increase the power of a laser beam, for example, we can have focusing. So this is a soliton dynamics, meaning that instead of this diffraction, we compensate this diffraction with this focusing effect, and the light is actually creating for itself an optical waveguide. So it's changing the refractive index for itself, and this is like this idea of gravity mass changing their own curved space-time. Okay. Usually in optics, we have local nonlinearities, meaning that we have a laser beam in a specific point, it will change the refractive index in this specific point. But I wanted something that will emulate gravity, so we need long range for that. So for an amplitude of the electromagnetic field, I would like to have some long change of the refractive index. So a way to implement that was using a thermal nonlinearity. And the physics here is very simple, everybody can understand that. If we shine light into a material, it is a bit absorbed inside, it raises the local temperature at this specific point. But we all know that there is a heat equation, and the temperature is actually going to change all around the bulk. If we have materials where your refractive index depends strongly on the temperature, what you get from this heat equation is a Poisson equation for this change of the refractive index. So we have laser absorbed in the medium, hitting the medium, and then changing its refractive index even far away. So we can have something like this long range, like gravity. If we couple this equation now to the equation I showed you before that described this evolution of the laser beam, so we have two coupled equations. You have this evolution of this laser beam inside this nonlinear thermal material. So here is exactly the soliton, but this is results from the experiments in the lab in Israel. We launch a laser beam for low power. There is diffraction. If you take a picture, an image here at the end, you will get this broadening. Now we increase the power, and we take another picture at the end, and we see that we have a focusing effect. So the light changed its refractive index for itself. So why is this sort of equation so good for us? Because they're exactly analogous to the Newton-Schrödinger. Okay, so here is the Schrödinger equation, we all know, but we have some gravitational potential here, phi. This gravitational potential, it's not an external potential. It comes from the fact that this quantum wave function, psi, has some mass density. So the source for this gravitational potential comes from the Newton equation, where this quantum wave function has some mass. So this is a quantum wave function creating gravity for itself. And the equation I just showed you with this thermal nonlinearity gives you exactly the same, where instead of dynamics in time, in Schrödinger, we'll have to study evolution in the z direction, our preferred axis. So the laser beam is propagating, it's like dynamics in time. And instead of having actual gravitational potential, we have a change of the refractive index delta n. With a different sign, because light likes to be where the refractive index is higher, like in an optical fiber. And this set of equations I showed you lies exactly here. And this model was studied theoretically for a long time. It was first suggested as some model for the collapse of the quantum wave function. I'm not sure who believes in that today, but it can give us some intuition toward this quantum gravity puzzle, and as far as I can know, it was never experimentally observed. I hope I'm right. Yeah.
Negative sign. That doesn't look good. Can
No,
you
it's
change
very
it?
good. No,
Can
it's
you change
compensating.
the
Yeah,
sign?
no, it compensates. You have here a minus.
Oh, there's a minus
and
there
you have
as
here a
well.
minus.
Oh, okay.
So
Fine,
it's just a
fine.
convention in
I
optics. It's
missed that,
exactly
yeah.
the same. So
Okay,
it's,
very good. Very
it's
good.
attractive potential.
Okay, so it is the same.
So there's a special value of the parameter in which you get exactly straight propagation of the,
Yes.
of the beam?
Yes,
And what happens for,
exactly specific power and width of your beam.
and for larger values, do you have some
Yes, so you can get,
collapses?
you can get too much focusing, which would be like, let's say, a collapse, but not really. And you can get that you don't have enough power, and then you have this problem.
Can you get a collapse to a black hole?
No, no. So then I will start breaking a lot of assumptions in my equation. For example, here, I assume that this is small in some way relative to the actual refractive index of the material. So this is a few percent or something like that. Otherwise, you will start losing the analog. You cannot derive this linear paraxial equation. So I can't have a black hole. I can already tell you that I can't have I believe I cannot have gravitational waves. I will explain later why I can't have all these things in the system. I will show you what we did have. So before getting to the actual system and the experiment, I need you to know one concept from optics, which is this idea of accelerating beams. So this is a solution that Michal Bejger actually found to the Schrödinger equation, to the free space Schrödinger equation a long time ago in 1979. It has the shape of an Airy function. And the unique thing about this solution is that it is accelerating in time, meaning that it preserves the shape of this Airy function, but the coefficient here looks like a minus t squared. Do you see that? It means that over time, this wave function will shift in space on a parabolic trajectory. This is just a solution, an analytic solution to the Schrödinger equation. But people decided to use this in optics. So using this analog, t becomes z in our paraxial wave equation, and then we can have bending beam in our labs. So if you launch this specific beam, specific amplitude and phase, you will get bending beams in your lab in free space. And this is the kind of beams I use in the experiment. And the reason it's nice to use them is first, they're non-diffractive. They don't have this broadening, like the Gaussian I showed you before. And second, they're very broad. They're extended beams, so we can see some long-range effect on them. So now we know that anything that happened to the structure of our beam relates to this interaction, the analogous gravitational interaction. Okay, one important thing about these beams, if we launch different beams in a lab, if we squeeze this beam, we get bigger bending, so we can control the trajectory of this beam in our lab. We decide to launch a specific beam, we get a different bending. And the story of how this started is that I went to this group, they were doing nonlinear optics, and I was solving these accelerating beams in this highly non-local nonlinearity I just told you about, and then I took the course of general relativity at the same time and thought, okay, maybe I can do some model of gravity
You didn't
in the
learn at
lab.
home?
I didn't learn at home. No, I was a bad student at home. Only when I went to the university I started to learn anything. Yeah, I have funny stories about that too. Okay. So this is the experiment built in the lab in Israel. So this is the laser beam. We split this beam into two beams. One of them is a strong beam, it's a Gaussian beam, and the other one is going here, and we have a phase mask which controls the structure of our beam. So you can see here that I have this 2D bending beam, and it can bend in space. And both these beams are focused inside this nonlinear sample where we have this thermal nonlinearity or gravitational interaction between them. And here is a movie that shows you what happens inside. So this is a linear simulation. We have this powerful beam and we have this bending beam, and they interact inside this nonlinear sample. And in the actual experiment, we just take these kind of images at the end of the sample and see what happened to the structure of these two beams. So we call this a star maybe in gravity, and this is our accelerating beam. Now I will show you some results. Okay, so the first thing we can do is to take a 1D cross-section of this accelerating beam and from this image at the end of the sample and see what happened to the shape of the beam during the interaction. So here you can see what happened in low power of the beams, but now I increase the power. Okay, so you can see that the beam is shifted, and this makes a lot of sense. The beam is actually shifted toward this powerful beam, exactly gravitational lensing in this Newton-Schrödinger equations. If we add more power levels now into the graph, and now I plot the gravitational lensing, this shift as a function of the power of the beams, I see that as I increase the power of the beams, there is more and more gravitational lensing, as we would expect. But there is one thing that is a bit surprising. There is something that looks like a saturation effect. So I increase the power of the beams. In gravity, this would mean I increase the mass, or I increase g of gravity. I would expect that we have more and more gravitational lensing of these two beams, one toward the other, but we don't see that. So this was a bit surprising at first. But now let's look closer into these results. So this is experimental results. Let's put these two beams one over the other. There is another difference. Not only that they're shifted, but also this beam is deformed. Can you see that? So this oscillation for low power is very different than the oscillation we achieve from high power. So this beam was also squeezed during the interaction. And this is exactly tidal forces. So we know that if we fall into a black hole, our legs are shifted downwards much faster than our head, right? We become a spaghetti. Here I have 2D gravity plus time, okay? So it's 2D gravity, specific boundary conditions, and when you solve this, you solve the geodesic equation, you find that you have squeezing of your beam. And this can actually explain the saturation effect I just showed you. So think about that. We have this very strong beam, and we have a second beam bending away from it. Now we increase the power, so it will be a bit shifted, gravitational lens toward the star. But now it's also deformed. And I told you before that if we squeeze the beam and launch the squeeze beam, it will bend away faster, right? If we control this amplitude and phase, the beam can actually bend away faster. So there is some interplay between this gravitational interaction and between this linear interference and this shape of this beam. So this initial condition we just launched changed a bit what we would expect from this attractive interaction to begin with. And we have also observed gravitational redshift, but I just don't have time, so you can ask me about this at the end. And maybe the most surprising effect was that I've seen that not only that we have this bending, but also the star itself, this powerful beam, is a bit shifted away from the bending beam. So it's a bit, we were in attractive interaction, but both beams are going away from one another. So at the beginning it looks weird, but then I simulated it in the computer, not in the experiment. And then what you see is that you have this trajectory of this bending beam, and you have this trajectory of this star, of this powerful beam. And why is it bending away? So it's very clear. What we have is a potential. So this is the change of the refractive index, but it comes from both beams. So both beams play a role. This is not a pump probe experiment. They both have a lot of power in them. So this is not exactly symmetric. We know that this bending beam is not symmetric at all. So if you now fold this and draw this graph, you see that there is some net force, so it's not the same, it's not symmetric. So this powerful beam that is localized here at the center will have some net force toward specific direction. What direction? the direction of this very long tail that this bending beam has. So what happened is that we have this bending beam bending away, and also the star feels this tail of this beam bending away from it. So it looks very weird, but it's all in the equations of this Newton-Schrödinger system. There is nothing you can say new over the equation, but there is maybe some new thing we did not expect. So now I would like to quote from a paper called "Is Quantum Gravity Necessary?" And here they talk about the idea this can explain the collapse of the quantum wave function, but this is not the point of what I'm trying to say. In the paper we can read, we need to look at more realistic initial profiles. It will be important to see how sensitive the collapse is to the shape of the initial wave function. We cannot yet rule out the possibility that the behavior we see is an artifact of the Gaussian initial conditions, and to see how the collapse time depends on the wave packet shape. So I don't want to talk about the collapse, but what I'm saying is that for 20 years, maybe people have been studying this system, but always taking spherical initial conditions or Gaussian initial conditions because it's easier, because then you can solve analytically or approximately analytically. And only because we combine these optical emulations with this system, we thought of using these very non-symmetric beams, and then new ideas of the saturation effect and this repulsion came. They just appeared in the experiment. So this is something I don't know if I would have found just in theory. So now I will switch to the second study I'm doing here at Harvard now. So this is a theoretical suggestion for something that can be done in an experiment that we have here at Harvard. And this is the idea of a quantum optical system that emulates quantum curved space. And I will get to this quantum metasurfaces idea. So what is the motivation? When I came here to Harvard, I wanted to shift from this nonlinear optics that was all classical to something quantum. Okay, so I said, okay, I know optics, let's go to quantum optics, and I'm interested in gravity, so what can be a nice idea? Maybe we can think of having something quantum in gravity. For example, in quantum mechanics, we have superposition state. Can we have superpositions of space-time? Can we emulate having one Schrödinger radius plus a coherent superposition with a different Schwarzschild values? Okay, so this was the idea. And instead of having this transformation optics, where light can propagate in a material with specific refractive index distribution and mimic some curved space, let's have quantum transformation optics. So we want epsilon here that relates to our metric to become an operator, a quantum operator. Yeah, already, yes.
Usually when you have two big systems, the experimental effects of quantum interference, according to the usual theory of quantum decoherence, is proportional to the exponential of the entropy of the, inversely proportional to the exponential minus the entropy of the system.
No, did you want to repeat that? Did you say?
This is the Schrödinger cat paradox,
Yeah.
right? Why don't we see the cat half up and cat half down? It's because the cat's been measured by a measuring device with many degrees of freedom, and the probability of actually somehow seeing some effect that knows that there's a cat half up and a cat half down, once it's been measured, is exponentially suppressed in the entropy of the measuring device.
Yeah.
So for two black holes to be suppressed, to measure an effect like that, you know, for Sag A star, the entropy is around 10 to the 80. So the probability of observing something that put it in a coherent superposition would be 10 to the minus 10 to the 80.
Right.
But
We can.
focus
So we
on
can
Sag.
measure it. I agree. I mean,
I thought
we
you
can
said
have-
superposition of
Okay,
two different
so-
short
Well, it could be
radius.
primordial. I mean,
No,
why
I'm
do it?
saying maybe we can measure it. That's okay. Can I emulate in a tabletop experiment this idea? This is the question. I don't know about measuring it. Maybe.
Well, if you don't focus on Sag A star, or if you focus on primordial black holes, you can imagine situations like that.
So I'm saying let's just imagine. This is the imagination slide. This part is the imagination slide.
Okay,
So
but I
this is
have
just
to
the
object
motivation.
because I think the defining characteristic of a black hole is something whose entropy grows like 1 over h bar in the classical limit. And I don't see any.
Okay, so let's forget about black holes.
But black holes means that
anything.
black hole. The word black in
Yeah.
front of black holes is that black means that light can't get out.
Right.
And the reason light can't get out of a black hole is that it would violate the second law of thermodynamics, because quanta of light have amount of entropy that goes like order 1. And if you decrease the mass of a black hole, you increase its entropy like 1 over h bar. So you don't see anything in a
Yeah.
classically as
I'm
black.
okay with that. This is okay. If you can wait with this, I think you won't have any problem. Because I'm not going to claim I did this. So
Okay.
now I'm giving a motivation of thinking, so do you think it's a fundamental problem, not with observing?
I do think
you
it's a
see some
fundamental
problem
problem.
of
I think
thinking-
I do think that by the time you did something to a black hole that you could measure this sort of thing, you shouldn't be calling it a black hole anymore.
Okay.
I would say
I'm
the
okay
same
with
thing,
that.
I would have the same objection to the various experiments that claim to
Yeah.
measure Hawking radiation and so on.
Okay, I'm okay with that. So let's proceed. I think you won't have a problem, but we can again touch it at the end. I will be happy to discuss it further. So the idea is to have, instead of this transformation optics, where light is traveling in some curved space we designed, to have this curved space being quantum, and this is again in the emulating system. So maybe there is no problem with what we're saying because this is just a motivation. But I will be happy to talk about it further at the end. So what I would like to have in the emulating system is now superposition of 2 different refractive indexes. So I want my light to see superposition of 2 different materials. So maybe this is why there is no problem with the black hole. This is not really a black hole, these are 2 different materials. So how can we do that? The idea is to have quantum mirrors. So think about an array of atoms so these atoms can have each one of them 2 different states. You have this purple state and this white state. And we can prepare this very interesting state of a superposition of these atoms being in a superposition of, you see, 1 white, 1 purple, 1 white, 1 purple, or the other one. And let's now look at the scattering of light from these atom arrays. And maybe we can have one time light is transmitted through this array, and if we prepare it in a different state, so one of our light modes is actually going back from this array, reflected. So I want you to think, instead of these refractive indexes, of a reflectivity being a quantum operator. Okay? And the ingredients to have this kind of system would be, first, to prepare this atom array state, which is not a simple task, and I will get to this in 2 slides. And the other one is to solve the scattering problem. So this is solving the Maxwell equation of light scattering from these atom arrays. So I will touch now these 2 different ingredients, but the second one first because it's easier to understand. So what we are solving is the Maxwell equations, but we assume that all these atoms are very close to one another, so we add an additional term, which means that that light can scatter from one atom to all the others. So we add an additional term. Light coming here can actually scatter from one atom to the other, and we need to take it into account because the distance between the atoms is very small. If we take this into account and we solve the scattering problem, we see that we have a collective effect of this atom array. So instead of each atom being able to maybe absorb a photon and the others do nothing, we have a collective effect of all of them, so there are collective modes, and then all the atoms act as one element. So this one element, which is the atom array, can be a mirror, it can be not a mirror, it can be maybe not a perfect mirror. And this is what we're trying to solve. Here at Harvard, there was a research that found that for specific A, for specific spacing, you can get a perfect mirror for the light. Okay? A perfect mirror for light being reflected. And the idea is to use this, but to go into R becoming an operator. So now we want to prepare this atom array in the superposition state. And I won't talk about this gravity analog for now. Maybe we go back to it at the end. Okay, so now we will talk about how can we prepare this kind of atom array. So now I relate to a specific experimental system that we have in Michal's lab, which is an atom array where each atom is trapped with a laser trap. Someone just got the Nobel Prize on this idea of the laser trap. And then we can actually excite each one of these atoms from the ground state to a Rydberg state. Okay, when the atoms are in this Rydberg state, they have van der Waals interaction between them. This can actually help to prepare very interesting states. For example, this is from a recent paper. what they were able to do here is prepare a state where one is in the Rydberg, one is in the ground. One is in the Rydberg, one is in the ground. I had it here. This is a bit more simple. One is up, one is down. One is up, and down. So in this experiment, one can control the state of this atom array. Now you can think about this superposition state because the same exact interaction can help us prepare this state. If they are all in the ground state, we can say they act as a perfect mirror, as we know that we can have from this paper a year ago. But if one is excited, one is not, one is excited, none is not, the mirror is ruined. So you have a superpositions of having a mirror or not a mirror. So I won't get into the technical details, but how can this help us? So first we can have an application to the emulation system, to quantum optics. And I'm sorry if I'm going a bit into details here. Do I have time? How much time do I have?
26.
Okay, that's okay. So the first thing we can do is quantum gates between this atom array and the light. So it's okay if you're not so familiar with quantum gates. I have a very nice thing here. So let's say we have a mirror now. Light is coming and reflected by the atom array. Okay, so if we were in this mirror state, a right propagating mode of the light is like a qubit, becomes a left propagating mode. Okay, we have changed the state of our photonic qubit. Now we will change the state of this atom array to a different state, and it's not a mirror anymore. So a right propagating mode continues being the right propagating mode. This is how this atom array controls the quantum information that we have on our photons. Okay, so, and if we look at this outlook of what can we do with this, what is the application, I showed you before, and here I relate to something I showed you in the first project. I showed you that I have this phase mask where I can take my beam and shape it to have a specific structure in space. So this was in the classical experiment. We're able to shape specific optical beams, specific laser beams. You can actually control this image with the classical computer. You can change the image each time and have different structures in space of this beam, but this is all classical. The idea here is that you can prepare a state of this atom array, you can scatter light from it, and then you can control quantum light. So you can structure the light, its quantum properties. You can have entanglement, and this can be used for metrology, for quantum computing, and many, many applications I won't go into, but now you have some control over your quantum structure of the light using this atom array preparation, which is easier. It's easier to control atoms than to control light. Okay, so I will summarize now. Yeah, sure.
Is that mirror itself a quantum superposition?
Again?
The mirror here in this bottom left.
The what?
You got a mirror there, right? Or whatever you call it.
The mirror, the mirror.
Mirror. Is that a quantum superposition or is that a classical system? I'm lost.
So, okay, you're lost. Yeah, it's okay. Sorry, maybe this was a bit fast. Okay, so if you have just a mirror, there is no quantum superposition. It's just a state. You can prepare the state very nicely. The challenge is to prepare this superposition. This is challenge. This does not exist now in the lab.
Okay.
This is a challenge.
But you are
There is a theoretical suggestion I have of how to do that.
Okay.
In a year or two, it will be, or maybe months.
But your discussion was assuming that you've got this superposition.
So yeah, I mean, you have a protocol.
Okay.
In the experiment, it can take time to do the protocol. Yeah, but it's using exactly the same interaction that was used to create this.
Okay.
I can give you
But as a
intuition.
superposition. Okay.
Yeah, I can give you intuition of how we can do that. For example, if you have one atom here, and it has two different states. In one state, it allows, then you have this preparation of state, okay? If this atom is in one specific, in a zero state, it enables this, and then you have this. But if it's in a different state, it does not enable this protocol, and then it keeps being in the same state. And then you can have this, but there are different ways of how to have this superposition state. Okay, so now I would like to summarize. So the first project was an emulated curved space created by mass itself using this non-local nonlinearity in optics, the first optical analog to the Newton-Schrödinger equations. We have experimentally observed different various gravitational effects, and I think most importantly, we have seen that if we structure the wave packets, we see things that are a bit not predictable, like the saturation effect and the repulsion that we have in this attractive interaction. And in the second study, we had emulation of quantum gravitational backgrounds for light. So I think it's not a problem because it's emulation specifically for light. I never claimed that I have the actual superposition of black holes. And this idea led us to this quantum metasurfaces, and this is a complete new scheme for quantum information that has application to the emulation system of quantum optics. That's it. So I will just thank my advisor at the Technion, Professor Moti Segev, and my collaborators there, and my mentor here, Professor Michal Bejger, and my collaborators specifically from ITAM, Igor Pikovsky and Hannes Bejger. Thank you very much.
In your summary, you said there were non-predictable effects like saturation, but then I thought earlier you said you were able to understand those from the equations. So
Yeah, so they exist in the equations. It's not that I added new terms into the equation. I just think that if you look at the equation, you don't expect to see them. So if we wouldn't have these specific initial profiles, but keep going with Gaussian initial conditions, spherical initial conditions, and studying the equation, I just think we won't see it. It's not that it doesn't exist in the equations.
But where does this all go? Is it just really cool stuff, or do you imagine this as some kind of an analog computer or something that you could
The second one, it's very good, because if you are able to have a quantum computer with the atoms, which is something that will happen, so photons are able to take your quantum information and carry it far away. So there are many applications where you need the quantum information on the photons. What is happening today is that you need to have a cavity, to put an atom inside a cavity, and to have very good coupling between your light and your specific atom. And what is suggested here is that you don't need a cavity. You have these atoms, you just shine light on them, and they scatter. So this is a new scheme for quantum information that has its own advantages. So hopefully, yeah, it started from motivation from this emulating gravity, but then it became an applicative project, I guess, because the collaboration is with a group that is very aimed to this quantum computer and quantum information applications. So it became, more.
Well, it's a very big field right now, and the government puts a lot of money into it.
Yeah, I heard. Yeah.
And the Chinese had this experiment, right?
Yeah.
With the satellite.
Entanglement with space.
Okay, I think it's time. A quick question, last question.
Yeah, it's kind of a weird question, but I was thinking about in the first experiment, the idea was, right, that you had a beam going through some medium and it changed the refractive index of the medium so that it emulates gravity.
Yeah.
So, would you ever hope to see gravitational dynamics by having multiple beams?
Would you say gravitational dynamics, what do you mean?
Meaning, would you see interactions of these different, well, they're both different beams sourcing their own index of refraction fields, so it would be interesting to look at the interactions between those.
And I'm not sure this will answer your question, but I do have one slide that maybe this is something similar to what you mean. Do you see this? Okay. So this is like one, maybe this is something that relates to your idea. So we have this, for example, rotating solitons you can have in the lab. And this will mimic something, so these are the rotating solitons, and this can mimic something like rotation of your space. And then you can send some probe beam that will start maybe orbiting around this. So yes, you can observe things like that. You always need to find the exact nonlinearity that will give you this, and the specific nonlinearity I worked would not give you this very nice thing that you can call frame driving. And so you need to find a bit of a different nonlinearity that will give you the effects.
Okay, let's thank our speaker.
Stuff anyway.
Yeah.